Şimdi ilk defa geldiğin için söyleyeyim ben bazı şeyleri, hani konuları bakarken böyle yayınlarda bakıyorum. Bunun ilk bölümünü bir önceki yayında yapmıştık. YouTube'a koydum onu, YouTube kanalıma. Şimdi de ikinci parçasını göreceğiz. Önceki bölümde pre-training modellere bakmıştık. Modellerin training. Şimdi post-training kısmına geçecek. Bir saatlik falan. 10'ar dakikalık bölüyorum, yorum yapmaya çalışıyorum. Öyle devam ediyorum. Bir saati tamamlamaya çalışıyoruz. O zaman beklemeden başlayalım. Vakit nakittir.
Stages in post-training are going to be computationally much less expensive. Most of the computational work, all of the massive data centers, and all of the sort of heavy compute and millions of dollars are the pre-training stage. But now we go into the slightly cheaper, but still extremely important stage called post-training, where we turn this LLM model into an assistant. So let's take a look at how we can get our model to not sample internet documents, but to give answers to questions. So in other words, what we want to do is we want to start thinking about conversations.
Şimdi önceki bölümlerde, şimdi 10 dakika sonra yorum yapacağım ama önceki bölümlerde biz hep autocomplete'e odaklanmıştık. Yani anlattığı şeyde onlar vardı. Sen bir şey veriyorsun, input, o devamını getirmeye çalışıyordu. Tokenizer'dan falan bahsetmişti. Şimdi burada soru soruyorsun, cevap veriyor falan. Biraz daha değişik bir formatı. Bakalım ne olacak.
And these are conversations that can be multi-turn, there can be multiple turns, and they are, in the simplest case, a conversation between a human and an assistant. And so, for example, we can imagine the conversation could look something like this. When a human says, "What is 2 plus 2?" the assistant should respond with something like, 2 plus 2 is 4. When a human follows up and says, "What if it was star instead of a plus?" assistant could respond with something like this. And similar here, this is another example showing that the assistant could also have some kind of a personality here, that it's kind of like nice. And then here in the third example, I'm showing that when a human is asking for something that we don't wish to help with, we can produce what's called a refusal. We can say that we cannot help with that. So in other words, what we want to do now is we want to think through how an assistant should interact with a human. And we want to program the assistant and its behavior in these conversations. Now, because this is neural networks, we're not going to be programming these explicitly in code. We're not going to be able to program the assistant in that way. Because this is neural networks, everything is done through neural network training on datasets. And so, because of that, we are going to be implicitly programming the assistant by creating datasets of conversations. So these are 3 independent examples of conversations in a dataset. An actual dataset, and I'm going to show you examples, will be much larger. It could have hundreds of thousands of conversations that are multi-turn, very long, etc., and would cover a diverse breadth of topics. But here I'm only showing 3 examples. But the way this works basically is assistant is being programmed by example. And where is this data coming from? Like 2 times 2 equals 4, same as 2 plus 2, etc. Where does that come from? This comes from human labelers. So we will basically give human labelers some conversational context, and we will ask them to basically give the ideal assistant response in this situation. And a human will write out the ideal response for an assistant in any situation, and then we're going to get the model to basically train on this and to imitate those kinds of responses. So the way this works then is we are going to take our base model, which we produced in the pre-training stage, and this base model was trained on internet documents. We're now going to take that data set of internet documents and we're going to throw it out, and we're going to substitute a new data set. And that's going to be a data set of conversations. And we're going to continue training the model on these conversations, on this new data set of conversations. And what happens is that the model will very rapidly adjust and will sort of like learn the statistics of how this assistant responds to human queries. And then later during inference, we'll be able to basically prime the assistant and get the response, and it will be imitating what the human labelers would do in that situation, if that makes sense. So we're going to see examples of that, and this is going to become a bit more concrete. I also wanted to mention that this post-training stage, we're going to basically just continue training the model, but the pre-training stage can in practice take roughly 3 months of training on many thousands of computers. The post-training stage will typically be much shorter, like 3 hours, for example. And that's because the data set of conversations that we're going to create here manually is much, much smaller than the data set of text on the internet. And so this training will be very short, but fundamentally, we're just going to take our base model, we're going to continue training using the exact same algorithm, the exact same everything, except we're swapping out the data set for conversations. So the questions now are, what are these conversations? How do we represent them? How do we get the model to see conversations instead of just raw text? And then what are the outcomes of this kind of training? And what do you get in a certain like psychological sense when we talk about the model? So let's turn to those questions now. So let's start by talking about the tokenization of conversations. Everything in these models has to be turned into tokens because everything is just about token sequences. So how do we turn conversations into token sequences is the question. And so for that, we need to design some kind of an encoding. And this is kind of similar to maybe if you're familiar, you don't have to be, with, for example, the TCP/IP packet on the internet. There are precise rules and protocols for how you represent information, how everything is structured together so that you have all this kind of data laid out in a way that is written out on a paper and that everyone can agree on. And so it's the same thing now happening in LLMs. We need some kind of data structures, and we need to have some rules around how these data structures, like conversations, get encoded and decoded to and from tokens. And so I want to show you now how I would recreate this conversation in the token space. So if you go to Tick Tokenizer, I can take that conversation, and this is how it is represented in for the language model. So here we are iterating a user and an assistant in this two-turn conversation. And what you're seeing here is it looks ugly, but it's actually relatively simple. The way it gets turned into a token sequence here at the end is a little bit complicated, but at the end, this conversation between a user and assistant ends up being 49 tokens. It is a one-dimensional sequence of 49 tokens, and these are the tokens, okay? And all the different LLMs will have a slightly different format or protocols, and it's a little bit of a wild west right now. But for example, GPT-4o does it in the following way. You have this special token called IM_start, and this is short for imaginary monologue, the start. Then you have to specify, I don't actually know why it's called that, to be honest. Then you have to specify whose turn it is. So for example, user, which is a token 1428. Then you have internal monologue separator, and then it's the exact question, so the tokens of the question. And then you have to close it, so IM end, the end of the imaginary monologue. So basically, the question from a user of what is 2 plus 2 ends up being the token sequence of these tokens. And now the important thing to mention here is that IM start, this is not text, right? IM start is a special token that gets added. It's a new token. And this token has never been trained on so far. It is a new token that we create in a post-training stage and we introduce. And so these special tokens like IM_sep, IM_start, etc. are introduced and interspersed with text so that they sort of get the model to learn that, hey, this is the start of a turn for, who is it the start of the turn for? The start of the turn is for the user. And then this is what the user says. And then the user ends. And then it's a new start of a turn, and it is by the assistant. And then what does the assistant say? Well, these are the tokens of what the assistant says, etc. And so this conversation is now turned into this sequence of tokens. The specific details here are not actually that important. All I'm trying to show you in concrete terms is that our conversations, which we think of as kind of like a structured object, end up being turned via some encoding into one-dimensional sequences of tokens. And so because this is a one-dimensional sequence of tokens, we can apply all the stuff that we applied before. Now it's just a sequence of tokens, and now we can train a language model on it. And so we're just predicting the next token in a sequence, just like before, and we can represent and train on conversations. And then what does it look like at test time during inference? So say we've trained a model, and we've trained a model on these kinds of data sets of conversations, and now we want to inference. So during inference, what does this look like when you're on ChatGPT? Well, you come to ChatGPT and you have, say, like a dialogue with it. And the way this works is basically, say that this was already filled in. So like, what is 2 plus 2? 2 plus 2 is 4. And now you issue what if it
Aaron şeyde söylemiştik abi de 10 dakikada bir yapıyorum hani videoyu fazla bölmemek adına. Şu anda geç 10 dakika dolduğu gibi bitirsin cümlesini açıklama yapacağım.
was times IM end. And what basically ends up happening on the servers of OpenAI or something like that is they put in IM start assistant, IM sep, and this is where they end it, right here. So they construct this context And now they start sampling from the model. So it's at this stage that they will go to the model and say, okay, what is a good first sequence? What is a good first token? What is a good second token? What is a good third token? And this is where the LLM takes over and creates a response. Like, for example, response that looks something like this, but it doesn't have to be identical to this, but it will have the flavor of this if this kind of a conversation was in the dataset. So that's roughly how the protocol works, although the details of this protocol are not important. So again, my goal is just to show you that everything ends up being just a one-dimensional token sequence, so we can apply everything we've already seen, but we're now training on conversations, and we're now
Burada durdurmuşken devam edeyim. Şimdi bazen böyle şeyde diğer videolarda izlerken şey oluyor. Böyle çok durdurulduğu zaman konsept sapıyor. Anlayamıyorsun. Şimdi elemanı anlamlı yerlerde bölmeye çalışıyorum. 10 dakikada oldu zaten. Şimdi burada önceki derste tek hedef vardı. Bu arada konuyu ilk defa şey yapan için videonun önceki bölümünü izleyebilirler. Burada GPT mesela ChatGPT'de olaylar nasıl dönüyor? Onun altyapısındaki şeyleri anlatıyor bu arkadaş Karpati. Önceki bölümde tek hedef şuydu. Elinde olan datasetini tokenize etmek, tokenlara çevirmek. Çünkü bu large language model herhangi bir işlem yapacaksa eğer bunların ortak bir alanda buluşması gerekiyor. Token'a çevirirken de bazı yöntemlerden bahsetmiştim. Onların detayına girmeyeceğim ama bir önceki bölümde sadece şey vardı. Sen bir şey yapmaya çalışıyorsun, sistem devamını getiriyordu. Burada ama bir conversation, yani user bir şey soruyor, arada asistan da devreye sokabiliyorsun. Sonra sana cevap veriyor. User soruyor, cevap veriyor. Peki buradaki yapı ne olacak? Yani öncekinde sen bir şey söylüyordun, devamı geliyordu. Şimdi sen bir soru soruyorsun, sana cevap geliyor. Bir de orada inference'dan bahsetti. Inference elindeki datadan sonra belli devamını üretme anlamına geliyor inference'da da. Burada yine hedef tokenize etmek ama biraz daha diğerinden farklı çalışıyor. Mesela Conversation'a baktığın zaman şu TikTokenizer diye bir proje var. Yani açık kaynaklı, source koduna bakabilirsiniz. Şöyle de bir tane Vercel uygulaması var. Burada girdiği mesela GPT-4'te nasıl çalıştığını anlatmaya çalışıyor. İşte bir diyalog koydu buraya. Diyalogda da bunu girdiği zaman karşı tarafta neye çevriliyor? Mesela I am start diye bir şey var. User, I am separator şey veriyor. Ya şu formatı kullanarak kim ne sordu, ne cevap vermem gerekiyor falan gibi bir şeye varmaya çalışıyor ama nihayetinde böyle özel bir format bile olsa, yani sen yukarıda bir diyalog girdin, aşağıdaki çevrilmiş halinden bahsediyorum. Buraya çevrilse bile yine bunlar bir token'a tekabül ediyor. Bak mesela I am start. O bir token'a tekabül ediyor. User var, I am sep var. Başka bir şeye tekabül ediyor. Yani günün sonunda bir önceki bölümde nasıl her şeyi tokenize edip bir sonraki adımı hesaplamaya çalışıyordu. Burada da conversation'da soru cevap yaparken yine aynı mantığı kullanıyor. Sadece tokenize etmeden önce arada bir tane step var. Şöyle bir çevrim. Onu da işte diyalog için falan kullanıyorlar. Bakalım bir sonraki adımda neye gidecek. Bu arada bir önceki bölümdeki o large, yani internet datasını kullanıp Fine Web'den falan bahsetmişti, hatırlayın. Yani ne kadardı? 300 terabayt mıydı? Tam boyutunu hatırlayamıyorum. Böyle kötü içerikten falan arındırılmış, işte korsanlıkla, suçla, cinsellikle bilmem ne, böyle kötü şeylerden arındırılmış web'in iyi taraflarını barındıran kısmın dataya Fine Web diyoruz. İşte o Fine Web üzerinde çalıştırıp LLM'in bir şeyler öğrendiğini düşünün. O prosesin aynısı buna da uygulanıyor. Niye peki buna da uygulayabiliyorum? Çünkü bunu da tokenize edebildiğim için. Mantık öyle işliyor. Önce otomatik tamamlaya bakmıştık. Şimdi diyaloğa bakıyoruz. Bakalım bundan sonra ne anlatacak? Abdurrahim, soruya abi sonradan geleyim. Şu videoyu bir şey yapalım. Halledelim.
basically generating conversations as well. Okay, so now I would like to turn to what these datasets look like in practice. The first paper that I would like to show you, and the first effort in this direction, is this paper from OpenAI in 2022. And this paper was called Instruct GPT, or the technique that they developed. And this was the first time that OpenAI has kind of talked about how you can take language models and fine tune them on conversations. And so this paper has a number of details that I would like to take you through. So the first stop I would like to make is in section 3.4, where they talk about the human contractors that they hired, in this case from Upwork or through Scale AI, to construct these conversations. And so there are human labelers involved whose job it is professionally to create these conversations. And these labelers are asked to come up with prompts, and then they are asked to also complete the ideal assistant responses. And so these are the kinds of prompts that people came up with. So these are human labelers. So list 5 ideas for how to regain enthusiasm for my career. What are the top 10 science fiction books I should read next? And there's many different types of kind of prompts here. So translate this sentence from to Spanish, etc. And so there's many things here that people came up with. They first come up with the prompt, and then they also answer that prompt, and they give the ideal assistant response. Now, how do they know what is the ideal assistant response that they should write for these prompts? So when we scroll down a little bit further, we see that here we have this excerpt of labeling instructions that are given to the human labelers. So the company that is developing the language model, like for example OpenAI, writes up labeling instructions for how the humans should create ideal responses. And so here, for example, is an excerpt of these kinds of labeling instructions. On a high level, you're asking people to be helpful, truthful, and harmless. And you can pause the video if you'd like to see more here. But on a high level, basically just answer, try to be helpful, try to be truthful, and don't answer questions that we don't want kind of the system to handle later in ChatGPT. And so roughly speaking, the company comes up with the labeling instructions. Usually they are not this short. Usually they are hundreds of pages, and people have to study them professionally. And then they write out the ideal assistant responses following those labeling instructions. So this is a very human-heavy process, as it was described in this paper. Now, the dataset for InstructGPT was never actually released by OpenAI, but we do have some open source reproductions that were trying to follow this kind of a setup and collect their own data. So one that I'm familiar with, for example, is the effort of Open Assistant from a while back. And this is just one of, I think, many examples, but I just want to show you an example. So so these were people on the internet that were asked to basically create these conversations similar to what OpenAI did with human labelers. And so here's an entry of a person who came up with this prompt. Can you write a short introduction to the relevance of the term monopsony in economics? Please use examples, etc. And then the same person, or potentially a different person, will write up the response. So here's the assistant response to this. And so then the same person or different person will actually write out this ideal response. And then this is an example of maybe how the conversation could continue. Now explain it to a dog. And then you can try to come up with a simpler explanation or something like that. Now, this then becomes the label, and we end up training on this. So what happens during training is that, of course, we're not going to have a full coverage of all the possible questions that the model will encounter at test time during inference. We can't possibly cover all the possible prompts that people are going to be asking in the future. But if we have a data set of a few of these examples, then the model during training will start to take on this persona of this helpful, truthful, harmless assistant. And it's all programmed by example. And so these are all examples of behavior. And if you have conversations of these example behaviors, and you have enough of them, like 100,000, and you train on it, the model sort of starts to understand the statistical pattern, and it kind of takes on this personality of this assistant. Now, it's possible that when you get the exact same question like this at test time, it's possible that the answer will be recited as exactly what was in the training set, but more likely than that is that the model will kind of like do something of a similar vibe. And it will understand that this is the kind of answer that you want. So that's what we're doing. We're programming the system by example, and the system adopts statistically this persona of this helpful, truthful, harmless assistant, which is kind of like reflected in the labeling instructions that the company creates. Now I want to show you that the state of the art has kind of advanced in the last 2 or 3 years since the InstructGPT paper. So in particular, it's not very common for humans to be doing all of the heavy lifting just by themselves anymore. And that's because we now have language models, and these language models are helping us create these data sets and conversations. So it is very rare that the people will like literally just write out the response from scratch. It is a lot more likely that they will use an existing LLM to basically like come up with an answer, and then they will edit it or things like that. So there's many different ways in which now LLMs have started to kind of permeate this post-training stack. And LLMs are basically used pervasively to help create these massive data sets of conversations. So I don't want to show, like, UltraChat is one such example of like a more modern data set of conversations. It is to a very large extent synthetic, but I believe there's some human involvement. I could be wrong with that. Usually there will be a little bit of human, but there will be a huge amount of synthetic help. Um, and this is all kind of like constructed in different ways. And UltraChat is just one example of many SFT datasets that currently exist. And the only thing I want to show you is that these datasets have now millions of conversations. These conversations are mostly synthetic, but they're probably edited to some extent by humans. And they span a huge diversity of sort of areas and so on. So these are fairly extensive artifacts by now, and there's all these like SFT mixtures, as they're called. So you have a mixture of like lots of different types and sources, and it's partially synthetic, partially human, and it's kind of like gone in that direction since. But roughly speaking, we still have SFT datasets. They're made up of conversations. We're training on them, just like we did before. And I guess like the last thing to note is that I want to dispel a little bit of the magic of talking to an AI. Like when you go to ChatGPT and you give it a question and then you hit enter, what is coming back is kind of like statistically aligned with what's happening in the training set. And these training sets, I mean, they really just have a seed in humans following labeling instructions. So what are you actually talking to in ChatGPT? Or how should you think about it? Well, it's not coming from some magical AI, like roughly speaking. It's coming from something that is statistically imitating human labelers, which comes from labeling instructions written by these companies. And so you're kind of imitating this, you're kind of getting, it's almost as if you're asking a human labeler. And imagine that the answer that is given to you from ChatGPT is some kind of a simulation of a human labeler. And it's kind of like asking, what would a human labeler say in this kind of a conversation? And it's not just like this human labeler is not just like a random person from the internet, because these companies actually hire experts. So, for example, when you are asking questions about code and so on, the human labelers that would be involved in creation of these conversation datasets, they will usually be educated, expert people. And you're kind of like asking a question of like a simulation of those people, if that makes sense. So you're not talking to a magical AI, you're talking to an average labeler. This average labeler is probably fairly highly skilled, but you're talking to kind of like an instantaneous simulation of that kind of a person that would be hired in the construction of these data sets. So let me give you one more specific example before we move on. For example, when I go to ChatGPT and I say, recommend the top 5 landmarks to see in Paris, and then I hit enter. Okay, here we go. Okay, when I hit enter, what's coming out here, how do I think about it? Well, it's not some kind of a magical AI that has gone out and researched all the landmarks and then ranked them using its infinite intelligence, etc. What I'm getting is a statistical simulation of a labeler that was hired by OpenAI. You can think about it roughly in that way. And so if this specific question is in the post-training data set somewhere at OpenAI, then I'm very likely to see an answer that is probably very, very similar to what that human labeler would have put down for those 5 landmarks. How does the human labeler come up with this? Well, they go off and they go on the internet and they kind of do their own little research for 20 minutes and they just come up with a list, right? Now, so if they come up with this list and this is in the data set, I'm probably very likely to see what they submitted as the correct answer from the assistant. Now, if this specific query is not part of the post-training data set, then what I'm getting here is a little bit more emergent because the model kind of understands that statistically the kinds of landmarks that are in its training set are usually the prominent landmarks, the landmarks that people usually want to see, the kinds of landmarks that are usually very often talked about on the internet. And remember that the model already has a ton of knowledge from its pre-training on the internet. So it's probably seen a ton of conversations about Paris, about landmarks, about the kinds of things that people like to see. And so it's the pre-training knowledge that is then combined with the post-training data set that results in this kind of an imitation. So that's roughly how you can kind of think about what's happening behind the scenes here in the statistical sense. Okay, now I want to turn to the topic of LLM psychology.
Şimdi arkadaşlar burada şey yapalım. Şimdi Human Labeler'dan bahsediyor. Aslında bu işin çok öncesinde bildiğiniz amelasyon, bu tarz mesela bazı sorulara nasıl cevap veriliyor. İnsanların bildiğin orada şeyden bahsetti. Bu Upwork ve Scale AI'dan bahsetti. İşte kiraladıkları bazı insanlara, işte bu alanda uzman olanlara işte soru, buna nasıl cevap verirdin gibisinden şeyler var. Onlar tabii bütün konuları bilmek gibi bir şeyleri yok. Onlar da gidip internetten araştıracaklar ki de. Bunlar bu datalar ürete bu birinci versiyonu, hani sorulara cevap veriyorsun falan. İkinci versiyonunda da bir LLM üzerinden bunu yaptırıyorsun ama LLM'in sana ürettiği datada bazı editlemeler yapabiliyorsun. Tamam, bunlar hani sanki insan olsaydı nasıl yapardığının bir şeyi, referans noktası gibi düşünebilirsin. Daha sonradan anlattığı post-training'de bu LLM'lerin post-training'de yaptığı şey, o human labeler'ların yaptığı şeyin istatistiksel olarak simülasyonu aslında. Yani mesela örnekte şeyi söyledi. Paris'te gezilesi nereler olabilir falan diye bahsetmişti. O eğer post-training datada varsa onu hemen sana sunabiliyor. Ama eğer post-training'de yoksa pre-training'de illaki vardır. Çünkü bahsetmiştik ya, Fine Web diye bir şey vardı. Orada terabaytlarca data var. Oradaki şeylerden hesaplayıp sana getiriyor. Yani sonuç olarak aslında pre-training ile post-training'in birleşiminde sana bir data sunuyor. Ama şeylerin görevleri büyük bu arada. Human Labeler. Ben ilk defa burada duydum. Çünkü evet, sana istatistiksel cevap veriyor ama bir referans da alabiliyor olması lazım. Çünkü sohbet ediyorsun yani bu şeyle, Large Language Model'la bir şekilde bize benziyor olması lazım. Hala daha bu şeyi kullanıyorlar mı bilmiyorum. Human Labeler'ları muhtemelen kullanıyorlardır. Ama öyle bir yöntemmiş. Yani daha çok insana benzesin diye böyle bir yöntem kullanıyormuş. Diğer 10
As
dakikaya
I like to
geçelim.
call it, which is what are sort of the emergent cognitive effects of the training pipeline that we have for these models. So, in particular, the first one I want to talk to is, of course, hallucinations. So, you might be familiar with model hallucinations. It's when LLMs make stuff up, they just totally fabricate information, etc. And it's a big problem with LLM assistants. It is a problem that existed to a large extent with early models from many years ago. And I think the problem has gotten a bit better because there are some mitigations that I'm going to go into in a second. For now, let's just try to understand where these hallucinations come from. So here's a specific example of of three conversations that you might think you have in your training set. And these are pretty reasonable conversations that you could imagine being in the training set. So, like for example, who is Tom Cruise? Well, Tom Cruise is a famous actor, American actor and producer, etc. Who is John Barrasso? This turns out to be a U.S. senator, for example. Who is Genghis Khan? Well, Genghis Khan was blah blah blah. And so, this is what your conversations could look like at training time. Now, the problem with this is that when the human is writing the correct answer for the assistant, in each one of these cases, the human either like knows who this person is or they research them on the internet and then they come in and they write this response that kind of has this like confident tone of an answer. And what happens basically is that at test time, when you ask for someone who is, this is a totally random name that I totally came up with, and I don't think this person exists, as far as I know. I just tried to generate it randomly. The problem is when we ask who is Orson Kovacs, the problem is that the assistant will not just tell you, oh, I don't know. Even if the assistant and the language model itself might know inside its features, inside its activations, inside of its brain, sort of, it might know that this person is like not someone that it's familiar with. Even if some part of the network kind of knows that in some sense, the saying that oh I don't know who this is not going to happen because the model statistically imitates its training set. In the training set, the questions of the form who is blah are confidently answered with the correct answer. And so it's going to take on the style of the answer and it's going to do its best. It's going to give you statistically the most likely guess. And it's just going to basically make stuff up. Because these models, again, we just talked about it, is they don't have access to the internet. They're not doing research. These are statistical token tumblers, as I call them. It's just trying to sample the next token in the sequence. And it's going to basically make stuff up. So let's take a look at what this looks like. I have here what's called the inference playground from Hugging Face. And I am on purpose picking on a model called Falcon 7B, which is an old model. This is a few years ago now. So it's an older model, so it suffers from hallucinations. And as I mentioned, this has improved over time recently. But let's say, who is Orson Kovacs? Let's ask Falcon 7B instruct. Run. Oh yeah, Orson Kovacs is an American author and science fiction writer. Okay, this is totally false. It's a hallucination. Let's try again. These are statistical systems, right? So we can resample. This time, Orson Kovacs is a fictional character from this 1950s TV show. It's total BS, right? Let's try again. He's a former minor league baseball player. Okay, so basically the model doesn't know. And it's given us lots of different answers because it doesn't know. It's just kind of like sampling from these probabilities. The model starts with the tokens, who is Orson Kovacs, assistant, and then it comes in here and it's getting these probabilities and it's just sampling from the probabilities and it just like comes up with stuff. And the stuff is actually statistically consistent with the style of the answer in its training set. And it's just doing that. But you and I experienced it as a made up factual knowledge. But keep in mind that the model basically doesn't know and is just imitating the format of the answer. And it's not going to go off and look it up because it's just imitating, again, the answer. So how can we mitigate this? Because, for example, when we go to ChatGPT and I say, who is Orson Kovacs? And I'm now asking the state-of-the-art model from OpenAI, this model will tell you, oh, so this model is even smarter because you saw very briefly, it said searching the web. We're going to cover this later. It's actually trying to do tool use. And it kind of just like came up with some kind of a story, but I want to just, who's Orson Kovacs? Do not use any tools. I don't want it to do web search. There's a well-known historical or public figure named Orson Kovacs. So this model is not going to make up stuff. This model knows that it doesn't know, and it tells you that it doesn't appear to be a person that this model knows. So somehow we sort of improved hallucinations, even though they clearly are an issue in older models. And it makes totally sense why you would be getting these kinds of answers if this is what your training set looks like. So how do we fix this? Okay, well, clearly we need some examples in our dataset where the correct answer for the assistant is that the model doesn't know about some particular fact. But we only need to have those answers be produced in the cases where the model actually doesn't know. And so the question is, how do we know what the model knows or doesn't know? Well, we can empirically probe the model to figure that out. So let's take a look at, for example, how Meta dealt with hallucinations for the Llama 3 series of models, as an example. So in this paper that they published from Meta, we can go into hallucinations, which they call here factuality, and they describe the procedure by which they basically interrogate the model to figure out what it knows and doesn't know, to figure out sort of like the boundary of its knowledge. And then they add examples to the training set where for the things where the model doesn't know them, the correct answer is that the model doesn't know them, which sounds like a very easy thing to do in principle, but this roughly fixes the issue. And the reason it fixes the issue is because, remember that like, the model might actually have a pretty good model of its self-knowledge inside the network. So remember we looked at the network and all these neurons inside the network. You might imagine that there's a neuron somewhere in the network that sort of like lights up for when the model is uncertain. But the problem is that the activation of that neuron is not currently wired up to the model actually saying in words that it doesn't know. So even though the internals of the neural network know, because there's some neurons that represent that, the model will not surface that. It will instead take its best guess so that it sounds confident, just like it sees in a training set. So we need to basically interrogate the model and allow it to say, I don't know, in the cases that it doesn't know. So let me take you through what Meta roughly does. So basically what they do is, here I have an example. Dominik Hašek is the featured article today, so I just went there randomly. And what they do is basically they take a random document in a training set, and they take a paragraph, and then they use an LLM to construct questions about that paragraph. So for example, I did that with ChatGPT here. So I said, here's a paragraph from this document. Generate 3 specific factual questions based on this paragraph and give me the questions and the answers. And so the LLMs are already good enough to create and reframe this information. So if the information is in the context window um, of this LLM, this actually works pretty well. It doesn't have to rely on its memory. It's right there in the context window. And so it can basically reframe that information with fairly high accuracy. So for example, it can generate questions for us like, for which team did he play? Here's the answer. How many cups did he win, etc. And now what we have to do is we have some question and answers, and now we want to interrogate the model. So roughly speaking, what we'll do is we'll take our questions and we'll go to our model, which would be, say, Llama uh, in Meta. But let's just interrogate Mistral 7B here as an example. That's another model. So does this model know about this answer? Let's take a look. So he played for Buffalo Sabres, right? So the model knows. And the way that you can programmatically decide is basically we're going to take this answer from the model and we're going to compare it to the correct answer. And again, the models are good enough to do this automatically. So there's no humans involved here. We can take basically the answer from the model and we can use another LLM judge to check if that is correct according to this answer. And if it is correct, that means that the model probably knows. So what we're going to do is we're going to do this maybe a few times. So, okay, it knows it's Buffalo Sabres. Let's try again. Buffalo Sabres. Let's try one more time. Buffalo Sabres. So we asked 3 times about this factual question, and the model seems to know, so everything is great. Now let's try the second question. How many Stanley Cups did he win? And again, let's interrogate the model about that, and the correct answer is 2. So here the model claims that he won 4 times, which is not correct, right? It doesn't match 2. So the model doesn't know, it's making stuff up. Let's try again. So here the model, again, is kind of like making stuff up, right? Let's try again. Here it says he did not win during his career. So obviously the model doesn't know. And the way we can programmatically tell again is we interrogate the model 3 times and we compare its answers, maybe 3 times, 5 times, whatever it is, to the correct answer. And if the model doesn't know, then we know that the model doesn't know this question. And then what we do is we take this question, we create a new conversation in the training set. So we're going to add a new conversation in the training set. And when the question is, how many Stanley Cups did he win? The answer is, I'm sorry, I don't know, or I don't remember. And that's the correct answer for this question because we interrogated the model and we saw that that's the case. If you do this for many different types of questions, for many different types of documents, you are giving the model an opportunity to, in its training set, refuse to say based on its knowledge. And if you just have a few examples of that in your training set, the model will know and has the opportunity to learn the association of this knowledge-based refusal to this internal neuron somewhere in its network that we presume exists. And empirically, this turns out to be probably the case. And it can learn that association that, hey, when this neuron of uncertainty is high, then I actually don't know. And I'm allowed to say that I'm sorry, but I don't think I remember this, etc. And if you have these examples in your training set, then this is a large mitigation for hallucination. And that's roughly speaking why ChatGPT is able to do stuff like this as well.
Burada durdurayım da şeyi de geçiyor. 10. dakikaya geçiyor. Burada halüsinasyonlardan bahsediyor bildiğin. Hani o hiçbir zaman bilmiyorum havasına kapılıyorduk ya. Bu LLM'ler istatistiksel olarak hesaplama yaptığı için yani dediği anlattığına göre yani o neural network'te içerideki bir nöronda muhtemelen bir şeyler olduğunu düşünüyor ve sen bir şey sorduğun zaman yanlış da olsa sana cevap veriyor. Çünkü istatistiksel hesapla yok diye bir şey diyemez. Ama bunu nerede sordu mesela? Çok güncel bir datayla eski bir modele soru soruyor. Orada her seferinde farklı cevap veriyor. Doğru bir cevap veremiyor bile. Sanki öyle bir şey varmış gibi. Olmayan bir karakterden bahsediyor ama Amerikan bir aktör falan diyor. Ama OpenAI'ya soruyorsun. OpenAI ne diyor? Hep up to date bilgileri olduğu için böyle bir şeyin olmadığını söylüyor. Ama biraz uzun uzun yazıyor ama olsun. Buna halüsinasyon diyorlar. Şey kısmı. Meta'da da bir tane white paper var. Onlar factuality diyorlar. İşte bir orana göre bu oranın altındaysa yok diyeceksin, üstündeyse var diyeceksin falan gibi bir yöntem getirmişler. Ama tabii işte öyle şeyler büyük modellerde, yani iyi olanlarda ya da büyük şirketlerin sağladığı modellerde oluyor. Burada da işte onu eğitmek için o tarz conversation'lar vermen lazım. İşte farklı farklı kategorilerde soru soruyorsun. İşte bu şundan dolayı benim bunun hakkında bilgim yok gibisinden conversation modeli verdiğinde bununla ilgili daha insana yakın bir şeyler söylüyor diyelim. Bir de şeyden bahsediyor burada. Zaten sorduğun sorunun cevabı senin sorunun içindeki kontekste varsa onu hemen cevaplayabiliyor. Yoksa şeye gidiyor işte o pre-training ve post-training datasına gidiyor. Evet, Karpati güzel anlatıyor bence de. Rust videoların devamı gelecek, evet. OpenAI videosu gelir mi bilmem, hani uzmanlık alanım olmadığı için, o yüzden ben hani derinlemesine öğrenmek için şeyden başladım. Genel bu videoların serisinin sebebi yayınların şu anlattığı LLM konusunu derinlemesine öğrenmek ve genel resmi görerek tabii. Daha sonra detaylı şeyler gelecek makine öğrenmesiyle alakalı.
So these are kinds of mitigations that people have implemented and that have improved the factuality issue over time. Okay, so I've
OpenAPI mi dedi? Ha, OpenAI. Ha, yanlış okumuşum ben. Konteks olduğu için OpenAI dedim.
described mitigation number one for basically mitigating the hallucinations issue. Now, we can actually do much better than that. It's instead of just saying that we don't know, we can introduce an additional mitigation number two to give the LLM an opportunity to be factual and actually answer the question. Now, what do you and I do if I was to ask you a factual question and you don't know? What would you do in order to answer the question? Well, you could go off and do some search and use the internet, and you could figure out the answer and then tell me what that answer is. And we can do the exact same thing with these models. So think of the knowledge inside the neural network, inside its billions of parameters. Think of that as kind of a vague recollection of the things that the model has seen during its training, during the pre training stage, a long time ago. So think of that knowledge in the parameters as something you read a month ago. And if you keep reading something, then you will remember it, and the model remembers that. But if it's something rare, then you probably don't have a really good recollection of that information. But what you and I do is we just go and look it up. Now, when you go and look it up, what you're doing basically is like you're refreshing your working memory with information, and then you're able to sort of like retrieve it, talk about it, or etc. So we need some equivalent of allowing the model to refresh its memory or its recollection. And we can do that by introducing tools for the models. So the way we are going to approach this is that instead of just saying, hey, I'm sorry, I don't know, we can attempt to use tools. So we can create a mechanism by which the language model can emit special tokens. And these are tokens that we're going to introduce, new tokens. So for example, here I've introduced two tokens, and I've introduced a format or a protocol for how the model is allowed to use these tokens. So for example, instead of answering the question, when the model does not, instead of just saying I don't know, sorry, the model has the option now to emitting the special token search start. And this is the query that will go to like bing.com in the case of OpenAI, or say Google search or something like that. So it will emit the query, and then it will emit search end. And then here, what will happen is that the program that is sampling from the model, that is running the inference, when it sees the special token search end, instead of sampling the next token in the sequence, it will actually pause generating from the model. It will go off, it will open a session with bing.com, and it will paste the search query into Bing. And it will then get all the text that is retrieved, and it will basically take that text. It will maybe represent it again with some other special tokens or something like that. And it will take that text and it will copy paste it here into what I tried to like show with the brackets. So all that text kind of comes here. And when the text comes here, it enters the context window. So the model, so that text from the web search is now inside the context window that will feed into the neural network. And you should think of the context window as kind of like the working memory of the model. that data that is in the context window is directly accessible by the model. It directly feeds into the neural network. So it's not anymore a vague recollection. It's data that it has in the context window and is directly available to that model. So now when it's sampling the new tokens here afterwards, it can reference very easily the data that has been copy pasted in there. So that's roughly how these tools function. And so web search is just one of the tools. We're going to look at some of the other tools in a bit. But basically, you introduce new tokens, you introduce some schema by which the model can utilize these tokens and can call these special functions like web search functions. And how do you teach the model how to correctly use these tools, like say web search start, search end, etc.? Well, again, you do that through training sets. So we need now to have a bunch of data and a bunch of conversations that show the model by example how to use web search. So what are the settings where you are using the search, and what does that look like? And here's by example how you start a search, end a search, etc. And if you have a few thousand maybe examples of that in your training set, the model will actually do a pretty good job of understanding how this tool works, and it will know how to sort of structure its queries. And of course, because of the pre-training data set and its understanding of the world, it actually kind of understands what a web search is. And so it actually kind of has a pretty good native understanding of what kind of stuff is a good search query. And so it all kind of just like works. You just need a little bit of a few examples to show it how to use this new tool. And then it can lean on it to retrieve information and put it in the context window. And that's equivalent to you and I looking something up. Because once it's in the context, it's in the working memory, and it's very easy to manipulate and access. So that's what we saw a few minutes ago when I was searching on ChatGPT for who is Orson Kovatz. The ChatGPT language model decided that this is some kind of a rare individual or something like that. And instead of giving me an answer from its memory, it decided that it will sample a special token that is going to do a web search. And we saw briefly something flash. It was like using the web tool or something like that. So it briefly said that, and then we waited for like 2 seconds, and then it generated this. And you see how it's creating references here. And so it's citing sources. So what happened here is it went off, it did a web search, it found these sources and these URLs, and the text of these web pages was all stuffed in between here, and it's not shown here, but it's basically stuffed as text in between here. And now it sees that text, and now it kind of references it and says that, okay, it could be these people, citation, it could be those people, citation, etc. So that's what happened here. And that's why when I said who is Orson Kovatz, I could also say don't use any tools, and then that's enough to basically convince ChatGPT to not use tools and just use its memory and its recollection. I also went off and I tried to ask this question of ChatGPT. So how many Stanley Cups did Dominik Hasek win? And ChatGPT actually decided that it knows the answer, and it has the confidence to say that he won.
Şeyler yazıyorlar da video mu durdu falan filan. Kimin ses mi gelmiyor? Nasıl ya? Dur. Bir saniye, şimdi şunu bir restart gibi bir şey vardı galiba. Bir bakayım hemen. Ee, Restart capture diyelim şöyle. Heh. Tamam. Şu an en son hali gözüküyor da ben zaten şey yapacağım, söyleyeceğim. Şöyle yapalım. Şimdi burada tool usage'dan bahsediyor arkadaşlar. Tool usage. Yani zaten bunu herhalde duymayan yoktur şeyde. Bu AI agent'ları kullanıyorsunuz. Hepsinde tool usage var. MCP falan kullanıyorsunuz. Onlardan bahsediyor. Soru sorduğunuz zaman bir şeyi eğer bulamazsa tool kullanımına gidebiliyor. Mesela bir kişiyi sordun. Web'den arama yapabiliyor. Aslında zaten kullandığımız terimler olduğu için pek de bir açıklama yapmaya gerek yok bu kısımda. Ama şeyden bahsediyor. Wagyu Collection vs. Working Memory diye. O Wagyu Collection, Recollection dediği hayal meyal hatırladığın şeyleri deniyor. Yani birebir insan beyniyle karşılaştıracak olursak burada yaptığımız. Bir de Context Window var. Context Window da aslında şey, çalışan memory. Yani hali hazırda hatırladığın şeylere de Context Window diyoruz. E, Mesela ne oluyor? Sen şeyi kapatıyorsun, session'ı kapatıyorsun. Claudio Code'la ya da bir şeyle çalışıyorsun. Session'ı kapatıyorsun. Başka bir tane session açtığın zaman bazı şeyleri sıfırdan öğrenmeye çalışıyor. Yani konteksinde kalmadığı için artık o. Ee, Burada da aslında şey, context window'u halihazırda çalışan, hatırladığın şeyleri gibi düşünebilirsin. Ama şey, tool kullanımına şey yapmış, odaklanmış burada bu anlatımda. Bir de onu demişsiniz. Tamam. Devam edelim.
So what I see very often on the internet is that people do something like this. They ask LLMs something like, "What model are you and who built you?" And basically, this question is a little bit nonsensical. And the reason I say that is that, as I tried to kind of explain with some of the under the hood fundamentals, this thing is not a person, right? It doesn't have a persistent existence in any way. It sort of boots up, processes tokens, and shuts off. And it does that for every single person. It just kind of builds up a context window of conversation, and then everything gets deleted. And so this entity is kind of like restarted from scratch every single conversation, if that makes sense. It has no persistent self, it has no sense of self, it's a token tumbler, and it follows the statistical regularities of its training set. So it doesn't really make sense to ask it, who are you, what built you, etc. And by default, if you do what I described, and just by default and from nowhere, you're going to get some pretty random answers. So for example, let's pick on Falcon, which is a fairly old model, and let's see what it tells us. So it's evading the question. Talented engineers and developers. Here it says I was built by OpenAI based on the GPT-3 model. It's totally making stuff up. Now, the fact that it's built by OpenAI here, I think a lot of people would take this as evidence that this model was somehow trained on OpenAI data or something like that. I don't actually think that that's necessarily true. The reason for that is that if you don't explicitly program the model to answer these kinds of questions, then what you're going to get is its statistical best guess at the answer. And this model had a SFT data mixture of conversations. And during the fine tuning, um, the model sort of understands as it's training on this data that it's taking on this personality of this like helpful assistant. And it doesn't know how to, it doesn't actually, it wasn't told exactly what label to apply to self. It just kind of is taking on this persona of a helpful assistant. And remember that the pre-training stage took the documents from the entire internet. And ChatGPT and OpenAI are very prominent in these documents. And so I think what's actually likely to be happening here is that this is just its hallucinated label for what it is. This is its self-identity, is that it's ChatGPT by OpenAI. And it's only saying that because there's a ton of data on the internet of answers like this that are actually coming from OpenAI, from ChatGPT. And so that's its label for what it is. Now, you can override this. As a developer, if you have an LLM model, you can actually override it. And there are a few ways to do that. So for example, let me show you, there's this Olmo model from Alan AI. And this is one LLM. It's not a top tier LLM or anything like that, but I like it because it is fully open source. So the paper for Olmo and everything else is completely fully open source, which is nice. So here we are looking at its SFT mixture. So this is the data mixture of the fine tuning. So this is the conversations data set, right? And so the way that they are solving it for the Olmo model is we see that there's a bunch of stuff in the mixture and there's a total of 1 million conversations here. But here we have Olmo 2 hard-coded. If we go there, we see that this is 240 conversations. And look at these 240 conversations. They're hard-coded. Tell me about yourself, says user. And then the assistant says, I'm Olmo, an open language model developed by AI2, Allen Institute of Artificial Intelligence, etc. I'm here to help, blah, blah, blah. What is your name? The Olmo project. So these are all kinds of like cooked up, hard-coded questions about Olmo 2 and the correct answers to give in these cases. If you take 240 questions like this, or conversations, put them into your training set and fine tune with it, then the model will actually be expected to parrot this stuff later. If you don't give it this, then it's probably a ChatGPT by OpenAI. And there's one more way to sometimes do this, is that basically in these conversations, and you have terms between human and assistant, sometimes there's a special message called system message at the very beginning of the conversation. So it's not just between human and assistant, there's a system. And in the system message, you can actually hard code and remind the model that, hey, you are a model developed by OpenAI, and your name is ChatGPT 4.0, and you were trained on this date, and your knowledge cutoff is this. And basically, it kind of like documents the model a little bit, and then this is inserted into your conversations. So when you go on ChatGPT, you see a blank page, but actually the system message is kind of like hidden in there, and those tokens are in the context window. And so those are the two ways to kind of program the models to talk about themselves. Either it's done through data like this, or it's done through system message and things like that. Basically invisible tokens that are in the context window and remind the model of its identity. But it's all just kind of like cooked up and bolted on in some way. It's not actually like really deeply there in any real sense as it would be for a human. I want to now continue to the next section, which deals with the computational capabilities, or like I should say, the native computational capabilities of these models in problem-solving scenarios. And so in particular, we have to be very careful with these models when we construct our examples of conversations. And there's a lot of sharp edges here that are kind of like elucidative, is that a word? They're kind of like interesting to look at when we consider how these models think. So consider the following prompt from a human. And suppose that basically that we are building out a conversation to enter into our training set of conversations. So we're going to train the model on this. We're teaching it how to basically solve simple math problems. So the prompt is, Emily buys 3 apples and 2 oranges. Each orange costs $2. The total cost is 13. What is the cost of apples? Very simple math question. Now, there are 2 answers here on the left and on the right. They are both correct answers. They both say that the answer is 3, which is correct. But one of these 2 is a significantly better answer for the assistant than the other. Like if I was a data labeler and I was creating one of these would be a really terrible answer for the assistant, and the other would be okay. And so I'd like you to potentially pause the video even and think through why one of these 2 is significant.
Because 2 orange at 4. Ben de beynimden böyle hesaplamıştım ama bu ne diyor? The total cost of the oranges 9. The cost of the apples. Hı? Ha, bu daha detaylı. Sağdaki daha detaylı tabii. Bakalım ne diyecek.
Significantly better answer than the other. And if you use the wrong one, your model will actually be really bad at math potentially, and it would have bad outcomes. And this is something that you would be careful with in your labeling documentations when you are training people to create the ideal responses for the assistant. Okay, so the key to this question is to realize and remember that when the models are training and also inferencing, they are working in one-dimensional sequence of tokens from left to right. And this is the picture that I often have in my mind. I imagine basically the token sequence evolving from left to right. And to always produce the next token in a sequence, we are feeding all these tokens into the neural network. And this neural network then gives us the probabilities for the next token in the sequence, right? So this picture here is the exact same picture we saw before up here. And this comes from the web demo that I showed you before, right? So this is the calculation that basically takes the input tokens here on the top and performs these operations of all these neurons and gives you the answer for the probabilities of what comes next. Now, the important thing to realize is that, roughly speaking, there's basically a finite number of layers of computation that happen here. So, for example, this model here has only 1, 2, 3 layers of what's called attention and MLP here. Maybe a typical modern state-of-the-art network would have more, like say 100 layers or something like that, but there's only 100 layers of computation or something like that to go from the previous token sequence to the probabilities for the next token. And so there's a finite amount of computation that happens here for every single token. And you should think of this as a very small amount of computation. And this amount of computation is almost roughly fixed for every single token in this sequence. That's not actually fully true, because the more tokens you feed in, the more expensive this forward pass will be of this neural network, but not by much. So you should think of this, and I think as a good model to have in mind, this is a fixed amount of compute that's going to happen in this box for every single one of these.
Şimdi bir 10 dakika daha doldurduk. Ona da bakalım. Explanation of self vardı bir tanesi. Hani soruyorsun kimsin nesin diye LLM'e soruyorsun ya. Orada işte eski modellerde gördüğünüz ben OpenAI tarafından geliştirildim falan diyor. Kimileri de sallıyor. Yani aynı hallucination'daki gibi. Sadece istatistiksel olarak sana bir şeyler sallıyor, yani öyle diyelim. Bunu ezmenin iki tane yolu var. Bir tanesi belki muhatap olduğunuz OpenAI'nin API'sini falan kullandıysanız eğer oradan bilirsiniz. Symptom mesajı herhangi bir soruyu sorarken soruyu soran user, cevabı veren asistan. Bir de soruyu sorarken yanında böyle şeyi bilgi olarak koyduğun kısımda da system mesajı. O system mesajına şeyi gömebiliyorsun. İşte sen OpenAI tarafından geliştirilmiş işte GPT-4 adında bilmem ne birisin diye söylediğinde model sana ona göre cevap veriyor zaten. System mesajıyla yapabiliyorsun. Override ediyorsun, yani bu rastgele verdiği cevabı override ediyorsun. Doğru cevabı versin diye. İkincisi de LLM modeline post training'de bunun gibi şeyler, conversation'lar veriyorsun. Mesela 200 bir örnek gösterdi olmadan. 240 tane conversation var. Sen kimsin? Onun bir cevabı var. Hangi modelsin? Onun bir cevabı var falan. Onu verdiğin zaman onunla ilgili soru sorduğun için sana düzgün cevabı vermiş olacak. Ondan bahsediyor. Bir de cevabı vermek için ekstra tokenlara ihtiyaç olma olayı vardı. Sen bir basit gibi bir soru soruyorsun. Yani normalde insan beyni olarak baktığında basit. Değil mi? Toplamda 13 dolar veriyor işte. Şeylerin orange'lar $2'şer. 2 tane alıyor. Elmaların şeyi ne kadar fiyatı diye soruyor. Normalde sen insan beyni olarak hemen cevap veriyorsun. Çok da basitmiş diyorsun ama bilgisayarda öyle bakmamak gerekiyor. Biraz daha farklı olmak gerekiyor. Cevabı doğru verebilmek için ekstradan düşünmesi gerekiyor. Ona da token harcıyor falan. İşte tek tek hesaplıyor içinden. Sonra ona göre cevap veriyor sana. Hatta bu şeye 2 tane cevabı ayırmıştı. Bana arada denk geliyor, size de geliyor mu bilmiyorum. ChatGPT'ye soru sorduğunuzda 2 seçenek sunuyor sana. Hangisini daha çok beğendin falan diye. Onu bir tanesini seçiyorsun. Sübtonik hoş geldin. İyiyim abi, senden sormalı. Şimdi son 10 dakikaya girdik. Onu da izleyelim.
Tokens. And this amount of compute cannot possibly be too big because there's not that many layers that are sort of going from the top to bottom here. There's not that much computationally that will happen here. And so you can't imagine the model to basically do arbitrary computation in a single forward pass to get a single token. And so what that means is that we actually have to distribute our reasoning and our computation across many tokens, because every single token is only spending a finite amount of computation on it. And so we kind of want to distribute the computation across many tokens. And we can't have too much computation or expect too much computation out of the model in any single individual token, because there's only so much computation that happens per token. Okay, a roughly fixed amount of computation here. So that's why this answer here is significantly worse. And the reason for that is, imagine going from left to right here, and I copy pasted it right here. The answer is 3, etc. Imagine the model having to go from left to right, emitting these tokens one at a time. It has to say, or we're expecting to say, the answer is space $, and then right here we're expecting it to basically cram all of the computation of this problem into this single token. It has to emit the correct answer, 3. And then once we've emitted the answer 3, we're expecting it to say all these tokens, but at this point we've already produced the answer, and it's already in the context window for all these tokens that follow. So anything here is just kind of post hoc justification of why this is the answer, because the answer is already created. It's already in the token window. So it's not actually being calculated here. And so if you are answering the question directly and immediately, you are training the model to try to basically guess the answer in a single token. And that is just not going to work because of the finite amount of computation that happens per token. That's why this answer on the right is significantly better, because we are distributing this computation across the answer. We're actually getting the model to sort of slowly come to the answer. From the left to right, we're getting intermediate results. We're saying, okay, the total cost of oranges is 4, so 13 minus 4 is 9. And so we're creating intermediate calculations. And each one of these calculations is by itself not that expensive. And so we're actually basically kind of guessing a little bit the difficulty that the model is capable of in any single one of these individual tokens. And there can never be too much work in any one of these tokens computationally, because then the model won't be able to do that later at test time. And so we're teaching the model here to spread out its reasoning and to spread out its computation over the tokens. And in this way, it only has very simple problems in each token, and they can add up. And then by the time it's near the end, it has all the previous results in its working memory, and it's much easier for it to determine that the answer is, and here it is, 3. So this is a significantly better label for our computation. This would be really bad, and it is teaching the model to try to do all the computation in a single token. It is really bad. So that's kind of like an interesting thing to keep in mind, is in your prompts, usually you don't have to think about it explicitly, because the people at OpenAI have labelers and so on that actually worry about this, and they make sure that the answers are spread out. And so actually OpenAI will kind of like do the right thing. So when I ask this question for ChatGPT, it's actually going to go very slowly. It's going to be like, okay, let's define our variables, set up the equation, and it's kind of creating all these intermediate results. These are not for you. These are for the model. If the model is not creating these intermediate results for itself, it's not going to be able to reach 3. I also wanted to show you that it's possible to be a bit mean to the model. We can just ask for things. So as an example, I gave it the exact same prompt, and I said, answer the question in a single token. Just immediately give me the answer, nothing else. And it turns out that for this simple prompt here, it actually was able to do it in a single go. So it just created a single, I think this is 2 tokens, right? Because the $ is its own token. So basically this model didn't give me a single token, it gave me 2 tokens, but it still produced the correct answer. And it did that in a single forward pass of the network. Now, that's because the numbers here, I think, are very simple. And so I made it a bit more difficult to be a bit mean to the model. So I said Emily buys 23 apples and 177 oranges. And then I just made the numbers a bit bigger. And I'm just making it harder for the model. I'm asking it to do more computation in a single token. And so I said the same thing. And here it gave me 5. And 5 is actually not correct. So the model failed to do all of this calculation in a single forward pass of the network. It failed to go from the input tokens, and then in a single forward pass of the network, a single go through the network, it couldn't produce the result. And then I said, okay, now don't worry about the token limit and just solve the problem as usual. And then it goes all the intermediate results, it simplifies, and every one of these intermediate results here and intermediate calculations is much easier for the model. And it's not too much work per token. All of the tokens here are correct, and it arises a right solution, which is 7. And it just couldn't squeeze all of this work. It couldn't squeeze that into a single forward pass of the network. So I think that's kind of just a cute example and something to kind of like think about. And I think is kind of, again, just elucidative in terms of how these models work. The last thing that I would say on this topic is that if I was in practice trying to actually solve this in my day-to-day life, I might actually not trust that the model did all the intermediate calculations correctly here. So actually probably what I do is something like this. I would come here and I would say use code. And that's because code is one of the possible tools that ChatGPT can use. And instead of it having to do mental arithmetic, like this mental arithmetic here, I don't fully trust it. And especially if the numbers get really big, there's no guarantee that the model will do this correctly. Any one of these intermediate steps might, in principle, fail. We're using neural networks to do mental arithmetic, kind of like you doing mental arithmetic in your brain. It might just like screw up some of the intermediate results. It's actually kind of amazing that it can even do this kind of mental arithmetic. I don't think I could do this in my head, but basically the model is kind of like doing it in its head. And I don't trust that, so I wanted to use tools. So you can say stuff like use code. And I'm not sure what happened there. Use code. And so, like I mentioned, there's a special tool, and the model can write code, and I can inspect that this code is correct. And then it's not relying on its mental arithmetic. It is using the Python interpreter, which is a very simple programming language, to basically write out the code that calculates the result. And I would personally trust this a lot more because this came out of a Python program, which I think has a lot more correctness guarantees than the mental arithmetic of a language model. So just another kind of potential hint that if you have these kinds of problems, you may want to basically just ask the model to use the code interpreter. And just like we saw with the web search, the model has special kind of tokens for calling, like it will not actually generate these tokens from the language model. It will write the program, and then it actually sends that program to a different sort of part of the computer that actually just runs that program and brings back the result. And then the model gets access to that result and can tell you that, okay, the cost of each apple is 7. So that's another kind of tool, and I would use this in practice for yourself. And it's, yeah, it's just less error prone, I would say. So that's why I called this section Models Need Tokens to Think. Distribute your computation across many tokens, ask models to create intermediate results, or whenever you can, lean on tools and tool use instead of allowing the models to do all of this stuff in their memory. So if they try to do it all in their memory, don't fully trust it and prefer to use tools whenever possible. I want to show you one more example of where this actually comes up, and that's in counting. So models actually are not very good at counting for the exact same reason. You're asking for way too much in a single individual token. So let me show you a simple example of that. How many dots are below? And then I just put in a bunch of dots. And ChatGPT says there are, and then it just tries to solve the problem in a single token. So in a single token, it has to count the number of dots in its context window. And it has to do that in a single forward pass of a network. In a single forward pass of a network, as we talked about, there's not that much computation that can happen there. Just think of that as being like very little computation that happens there. So if I just look at what the model sees, let's go to the LLM, go to tokenizer. It sees this, how many dots are below, and then it turns out that these dots here, this group of, I think, 20 dots, is a single token. And then this group of whatever it is another token. And then for some reason they break up as this. So I don't actually, this has to do with the details of the tokenizer, but it turns out that these, the model basically sees the token ID, this, and so on. And then from these token IDs, it's expected to count the number. And spoiler alert, it's not 161, it's actually, I believe, 177. So here's what we can do instead. We can say use code. And you might expect that, like, why should this work? And it's actually kind of subtle and kind of interesting. So when I say use code, I actually expect this to work. Let's see. Okay, 177 is correct. So what happens here is I've actually, it doesn't look like it, but I've broken down the problem into problems that are easier for the model. I know that the model can't count. It can't do mental counting. But I know that the model is actually pretty good at doing copy pasting. So what I'm doing here is when I say use code, it creates a string in Python for this. And the task of basically copy pasting my input here to here is very simple, because for the model, it sees this string of, it sees it as just these 4 tokens or whatever it is. So it's very simple for the model to copy paste those token IDs and kind of unpack them into dots here. And so it creates this string, and then it calls Python routine.count, and then it comes up with the correct answer. So the Python interpreter is doing the counting. It's not the model's mental arithmetic doing the counting. So it's again a simple example of um, models need tokens to think, don't rely on their mental arithmetic, and that's why also the models are not very good at counting. If you need them to do counting tasks, always ask them to lean on the tool. Now,
Şimdi bu son 10 dakikayı da bitirmiş olduk. Burada bahsettiği şey önemliydi aslında. Bu hesaplama yaparken mesela şöyle bir şey sorusu sormuştu, matematik sorusu. Eğer LLM model bunu aklında yapmaya çalışırsa hataya düşebilir. Mesela birinci soruda, birinci versiyonda the answer is $3 diyor. Halbuki cevabı bitmiş. Ama ondan sonra yine başka bir şeyler söylüyor. İkinciye baktığın zaman ara hesaplamalar yapıyor, sonra cevaba varıyor. Aslında doğru olan bu. Yukarıda bir neural network vardı. Hani bu tokenların o işlemden geçip, katmanlardan geçip cevabı üretmesi olayı. Bu iş böyle aritmetik işlemleri eğer tek token'da yapmaya çalışırsan ki burada öyle yapmış. Hemen $3 demiş. Tek token demeyelim de iki tane. İki token'a tekabül ediyor. Bir dolar, bir 3. Bu tarz yerlerde yanlış çıkma ihtimali çok yüksek. Ama token'lara bölerse mesela ilk önce birinci parça sonra ikinci parça sonra hepsini birleştirirse o neural network'taki hesaplama çok daha kaliteli bir çıktı veriyor. Sonradan ama bahsettiği şu, bunları böyle sayılarla özellikle sayılar büyüdüğünde çok fazla iyi yapamıyor. Onun yüzden de bu arkadaş Karpati diyor ki her seferinde kod kullan. Kod kullan dediği için ekranda görüyor hangi kodu kullandığını. Orada verify ediyor. Koddan yanlış çıkamaz zaten. Hesaplamaya formülü doğru koyduysa cevap da öyle olacaktır. Onu yapıyor. Bir örnekte de noktaları sayma olayı. Yine tek token'da yapabildiği için ya da yapmaya çalıştığı zaman orada fail ediyor. Çünkü sayma diye bir şey yok orada LLM'in. Ama kodla yap dediğin zaman o noktaların tamamını alıyor. Python'daki mesela noktayı say ya da verilen karakterleri say fonksiyonu çağırıp direkt oradan yapabiliyor. Bugün de anlattıkları bunlardı. Yani 2 saatlik bölümünü bitirmiş.